Okay. I have to tell you that we're going to be doing the hair thickness on Wednesday, rather than today. I switched it with another interactive activity today because I thought it would fit better in the sequence. It'll make more sense by the time you get to write your lab reports. Okay? So you can save your hairs. I know some of you plucked them already earlier today. You can either save them for Wednesday, or you can get another one Wednesday. So today, the focus is on light sources. Okay, what kinds of things generate light? And we're going to start talking about not so much light tissue, but light matter interactions. Okay, and then what will happen Wednesday is we'll continue with the light matter interactions. We'll start right off with measuring your hair thickness, and we'll move on with more specifics about how lasers interact with tissue. Then we'll move on to basic biology, and then tools for detecting light, and that'll cover the introductory period of the course, and then we'll go into more specifics. So what are the main points for today? There are various sources of light, and each of them has specific characteristics. What are some characteristics of light that you might want to be thinking about? Frequency, okay, or color, if they happen to be in the visible spectrum.
Wavelength.
Wavelength, definitely related to frequency, as we remember from the equation last time. Somebody mentioned absorption. Absorption is how light interacts with something. Bless you. We're thinking more about just the light itself, just all by itself. What are some characteristics? Yes? Intensity, the amount of energy it can put out. Any other ideas?
Particle wave duality.
Particle wave duality in what sense?
It's just a characteristic.
It is a characteristic. And it has an impact on certain things like measuring your hair thickness, but we'll be talking about that next week. Anything else? We talked about intensity. We talked about color, wavelength, frequency. Anything else you can think about?
Momentum.
Momentum. That's related to the energy. Okay. Anything simpler, like different ways of generating. Can you think of any varieties in how light might be generated? Like, how is the sun generating light? Fusion. So there's a lot of heat associated with it, right? So can you think of anything else, any other ideas? Any other characteristics of light you might be thinking about, you might look at? That's okay. We're going to get into that exactly. Then today we're going to then do a hands-on. We're going to observe the characteristics of various light with these handy-dandy spectrometers. And then we're going to look at the basics of how light interacts with matter. And the interesting thing is that light interacts with matter in a variety of ways simultaneously. Okay? Light can reflect, light can refract, light can be absorbed, all at the same time. Okay? All those things can happen simultaneously. And there's many more things that can actually happen simultaneously. So, first I'm going to give you this handout. You guys are going to have 15 minutes to do page 1 and page 2. Okay? You're basically, this handout is for your benefit. It'll be relevant when you go and take the exams or quizzes. So I suggest that you really do fill it out. And what I asked you is for you to think about yourself for a moment about some different characteristics of light, what you know about those light sources. And then I'd ask you on the second page to share some of your ideas and write down any other new thoughts you came up with. Okay? Just like so. For the second part, we're going to talk to you about what's new, what you like to talk to. So I would say take that's 7 or 8 minutes. Think about it by yourself, and then take another similar amount of time talking to your partner or to somebody near you. You're welcome to talk to more than one person if you'd like. Anyone want to offer a thought about one of the light sources? Want to say something about a light source? Pick any one of those on the list. Yes.
The light source something that they chemical reactions.
Excellent. Chemical reactions. Excellent, Katie. Okay, anything else? Anyone else want to say something? Yes. Sunlight is blue. Is that what you said? In what sense? Okay.
I mean, isn't it white clothes all colors, so technically there's blue in there?
There is blue in there. Definitely. Blue is in there. But there is all colors. Anything else? Yes.
The white lights have all the frequencies.
The white lights have all the frequencies in the visible spectrum. Thank you, Rich. Yes.
Lasers have just one frequency or a very, very narrow band of frequency and increasing frequency.
Thank you, Sam. That's right. Okay, anything else? One more?
The white LEDs are a combination of all the other LEDs to make white light.
The white LEDs? Okay. Sorry?
The phosphors in the white LEDs are the same phosphors that are in the tricolor or three RGB LEDs, but then they're all just in the same LED.
So he brought up the word phosphor. We're going to be talking about that. White LEDs can be done with phosphors or can be done without phosphors. There's two different ways of doing it. You can make white LEDs with red, green, and blue LEDs together, shining at the same time, focused, or you can make it with phosphors and a blue or ultraviolet LED.
But don't regular like RGB LEDs use a phosphor to convert the infrared light from the diode into visible light?
No, you can't convert infrared to visible.
Okay.
Very, very inefficient. You have to convert UV into visible.
Okay.
We're going to talk about that. That's what you're doing overhead on your with these fluorescent lights. Okay? Any other thoughts or questions? Yes.
Well, I recommend LEDs from screens, like on computers or cell phones. So I thought maybe it has something to do with generating a lot of pixels or taking in multiple light.
So most computer laptop screens and your bigger flat screens use fluorescent tubes to backlight the screens. The newer ones use LEDs because LEDs give a more uniform range of color and don't use up quite as much energy. So they allow more different colors for the given pixels, but not necessarily more pixels. That's a function of how the panel is constructed. Okay? Thank you, guys. Those are all very good comments. So, here's some different sources of light that we're going to be discussing. We're going to be discussing incandescent, which is basically heating something up. Okay? You guys remember how I brought that camera and I saw each of you, I could see your temperatures, and I could see you light up? Okay? You were emitting in the far infrared. Well, if I heat up something hot enough, if I was to heat you up to 4,000 or 5,000 degrees Kelvin, you'd give off white light. What appears to us as white light. Now, it wouldn't be very pleasant to do that, but basically when you burn something hot enough, it gives off white light. We're going to talk about electroluminescence, like light-emitting LEDs, diodes, LEDs, laser, fluorescence, which is light emission. You take in high-energy light and you re-emit lower-energy light. We're going to be talking about phosphorescence, which is very similar to fluorescence, but persists longer in time. And then we're going to talk about chemi and bioluminescence, like the firefly, and black body radiation, which is a pure form of incandescence. Okay? So, don't worry about having to write all this down. This will be passed. It will be on the online. I'll be putting that up. So, incandescence. What is it and how does it work? The basic idea behind incandescence is that if I heat something hot enough, it's going to give off a whole bunch of radiation. Now, incandescent light bulbs, you know, these guys right here. You guys remember the nice round light bulbs? Those are incandescent light bulbs. The moment I flip that switch, electricity courses through the light bulb, heats up a filament, roughly to somewhere in the neighborhood of 2,500, 2,600, sometimes 3,000, it varies, Kelvin, which is very hot. That heat makes energy be emitted in terms of electromagnetic radiation. That electromagnetic radiation covers the spectrum, giving us the perception of the color white. Similar to what the sun does, effectively. Okay? It's hot, gives off a whole range of wavelengths. We see that collection of wavelengths as appearing the color white. Now, you guys notice that incandescent bulbs make things look kind of yellowish? That just means they have more colors that tend to give you that overall impression when mixed together. Some halogen bulbs look more bluish or colder. Okay? It's just the mixture, just the temperature at which the filament is glowing gives a slightly different mixture, and you'll see, I'll show you what the emission spectra look like from those things, and you can tell that. Now, the reason that the light bulb works is because that filament has very high electrical resistance. When the electricity is pushed through it, it gives up the heat. So it's effectively like the electrons are trying to push through that stuff. Because they're pushing and struggling, they're causing heat to build up, and that heat gives off the light. Okay? Now, problem with incandescent bulbs is that the majority of the energy is given off as heat. Because it makes a whole range of wavelengths, not just the visible wavelengths, but it also makes a whole bunch of infrared radiation, which is lost as heat. That's why light bulbs are not all that efficient. About 90% of the energy put into a light bulb is given off as heat. And usually light bulbs we want not as heat sources, but as light sources. So that's what makes them not so efficient. Now we turn to LEDs. Here are little keychain LEDs, come different colors. Here's blue. Yes?
Do you reckon incandescent?
Sure.
Is that what they make heat lamps?
Effectively, heat lamps are the same thing. It's just that the material is such that it glows red. So the temperature that material is made out to be, the majority of the radiation that's emitted is in the red to the infrared. They're not wasting energy giving off white light. You're seeing the tail of the infrared radiation, because infrared is right next to red. So you see a little bit of the red, but the majority of the energy is given off in the infrared. And it's the same thing. You pass electricity, and the temperature at which that filament gets makes it emit heat, what we perceive as heat. Okay? That's why all those radiant heaters glow red like that. And you'll see in a second what temperature those get to. This is a violet LED. Here's a red LED. Here's a white LED. Okay? You can make pretty much all the colors of the rainbow now with LEDs, as well as some ultraviolet, low energy ultraviolet, and infrared. Infrared LEDs are commonly found where? Remote controls. Okay? Pretty much all remote controls. And again, you could see the remote control lighting up if you use your camera. One of your little digital cameras, pocket cameras, you can look, and on the screen you'll see it light up. Because those things are sensitive to near infrared. Okay, now, pretty much these are semiconductors. So what happens is, those of you who have had some physics or electronics, you have an N-type and a P-type semiconductor sandwiched against each other. You pass electricity through. That difference in those two materials causes a jump, an energy jump, to go from the P side to the N side, that emits energy in the color of the LED. Okay? So this one emits higher energy, this one's lower energy, and it just has to do with what materials you use in that junction. Yes?
Are neon lights kind of like LEDs?
Neon lights are actually a different process. It's a gas. So it's a gas that you electrically stimulate. The electricity causes excitation of the neon atoms, which then come back down and relax and give off the light. So it's a bit of a different process. Neon lights are closer to these fluorescent lights. Okay. The only thing about these fluorescent lights is they don't give off nice colors. They give off ultraviolet, which then interacts with something on the outside coating to create the white light. Neon lights don't have that. The gas that they have in there, when it's excited, gives off a color, a specific color. Okay, so 2 to 4 times more efficient than incandescents. And the reason we say they're more efficient than incandescent is because you notice they give off virtually no heat. You don't feel heat from LEDs, okay? Or very little. Okay? You guys see LEDs all the time in your traffic lights? 10 years ago, you didn't have traffic lights made out of LEDs. That was very, very rare. You now see them in backlights of cars, you see them in traffic lights, you see them in Christmas lights. That's been the big thing in the last 2 or 3 years. Because they use way, way less energy. Okay? And they also tend to last a very long time. Okay? And they come in a lot of different shapes and sizes. You can just see some small variety here. Almost all of your electronics that have a little light that might go yellow, red, green, whatever, those are LEDs. Okay? Then we have the laser. Okay. The laser. What makes laser stands for this, by the way, light amplification through stimulated emission of radiation. What makes a laser very interesting is that it's monochromatic. What does that mean? Any ideas? One color. Mono, one, chroma, color, one color. It's coherent. By coherent, what I mean here is that every photon, if I know where one photon is traveling, I can figure out how all the other photons are related to it. So in a sense, one simplistic way of thinking about it is that they're all the waves are traveling together. But the reality is that every wave can predict how the other waves are traveling. Okay, so they're all predictable. I can predict how these waves will behave. They don't change in the way they're traveling. They're directional. Notice I can point it. It stays fairly sharp as a point. It can travel in a straight line. Okay? It's not going everywhere like an incandescent light would. Incandescent lights spread their photons everywhere. This is very directional. It can focus to a few hundred nanometers. So it can focus into a very, very tiny spot, which means a very high power. It means a lot of photons concentrated in a very small spot. And I can range the lasers from ultraviolet to visible to infrared, and I can even have tunable lasers that I can change some property of the laser and it changes color. And we even have X-ray lasers now. Okay? So you can pretty much make lasers, they're very different sizes. They're not all these little handheld pocket things, but I can make them all kinds of different wavelengths. And I can pulse them down to femtoseconds. Okay? You guys remember what femto is? Nano was 1 times 10 to the minus 9th. Pico is 1 times 10 to the minus 12th. Femto is 1 times 10 to the minus 15th seconds. Now, what's interesting about that is that I can make very, very precisely timed pulses. And because I can make them very short, I can pack a lot of energy into a little short amount of time. How does it work? Okay, so I'm going to go to an animation here. Get this animation up. Okay. This is a website that you can go back to and read the whole piece, but it goes through and discusses the laser. So, notice what happens when I send photons and I excite an atom. One gets absorbed, it excites it, sometimes gets kicked off. Did you notice what's happening every once in a while? There's a different type of event happening. Two come off at the same time, okay? So if I pump energy in the form of light into an atom, into a collection of atoms, sometimes that's absorbed and then re-emitted. Sometimes it's absorbed, and when another photon comes and hits it, both get re-emitted together. Okay? That re-emission together is critical for making a laser. So let me keep going forward. This is pretty funny if you want to read it. So I can go here and I can do it now. An energy pump here is basically a light source. And you'll notice that some of them are getting green, and you'll notice that you're getting some emission. And sometimes they're emitting together, and they're emitting, though, in all different directions. You guys notice that? Okay. So that's two elements I need for a laser. I need a light source, and I need some kind of atoms that get excited.
Is it really hard for when they hit the atoms because they're so small? Or?
For the photons?
Is it hitting the nucleus, or?
No, it has to be. It has to basically excite an electron. So there's a cloud. That energy has to somehow be added. It has to be this exact right amount of energy to excite an electron to a higher energy state, to move the electron away further from the nucleus. So what you do when you're creating a laser is you make sure that those two things are tuned, so that the light that you're pumping in is exactly the energy that you need to excite those atoms. So now we do it this way. I put in a lot of energy. And what I have here is I have a one-way mirror here that allows the energy to come in, but acts as a mirror and bounces, and this is a 95% mirror. So what I mean by that is every once in a while it lets a certain amount of the photons through. And I don't know if you're seeing there's a buildup, and what happens is basically the atoms are getting excited. As the atoms get excited, every once in a while I have that event where there's two of them leaving off. And now there's just more and more and more atoms doing that. Because as two leave, they go and then they bounce and then they have another chance to hit. So because of these mirrors, I'm giving them more chances to hit and bounce off. Yes?
Why aren't they coming out the side anymore?
They should be. They're just simplifying the model here.
Okay.
There are some going off to the edges and are lost. So it isn't not a very efficient process. Okay? But the idea is, remember, in a laser, you've got, of these atoms, gazillions of these atoms, okay, in this space that you're causing to laze. And you've also got a tremendous large number of photons. So this is happening, and a certain number of them are leaving, and they're leaving together. They're uniform. They've all come from the same process. And that's this light that comes off of this laser. Okay? You've caused lasing to happen. It's kind of like, if I just had one in there, it couldn't do much. But because I have such a huge collection of atoms, you get this, okay, I was excited, another photon hit me, we both left together, and now together we're hitting another atom that was excited, and now we're going to go off and be 3, and then we're going to go off and be 4, and then we're going to go off and be 5, and we're going to keep bouncing back and forth until we get as many of these out. And that's going to be the laser beam that lasers out. Okay? Now, I have a more elaborate simulation for those of you who want to see it. I'm not going to show it today, but if you're interested, I can tell you where to find that. And there's different ways you can look at this. You can also look at it as waves. Those are the photons, and there's higher energy inside, but some energy gets out, and a wave gets to escape. The wave view is a little bit more complicated, a little bit harder to understand. Okay. This is just basically showing you the same thing, except in this case, what they show is a flash tube that sends energy, photons, into a piece of ruby. This is a ruby laser. So, it's the same idea again. You've got excited atoms. You've got the mirrored surfaces. Here you've got some light emitting off the sides, but some of it hits the mirrors, goes back and forth until it exits, and then it comes out, and the laser beam comes out. Okay? Again, you need to have a source of energy, source of photons coming in. You need to have a source of atoms that absorb that energy and laze, effectively get this multiplication factor going where you've got 2 coming out, and those 2 excite another, and those excite another, and those excite another, until the energy comes out and creates your laser beam. Question? Okay. So now we go into fluorescence. So fluorescence is basically the property of some atoms and molecules, to absorb high energy light, relax a little bit through usually vibrations, and then re-emit light of lower energy. Okay? I don't get energy for nothing. So I have to put in higher energy in, and I get lower energy out. Okay? Now, these bulbs above our heads, those are fluorescent bulbs. In there's a gas, mercury gas, or a variety of different gases, but mercury is a standard. It's excited by electricity. That gas is stimulated and gives off ultraviolet light. Now that would make a really lousy light bulb, right? If these things just generated ultraviolet light, we'd just be getting sunburns in here. We wouldn't see anything, but we'd be getting sunburns. Wouldn't be the greatest thing, right? So what they do is on the inside coating, You guys ever busted one of these? You ever taken one of these and shattered them and you just go, and you get all this powder going everywhere? Okay, because they're under pressure. You get all this powder. Well, that powder is very similar to what you have in your laundry detergent. It takes in high energy ultraviolet light and converts into different colors. And you guys are going to see exactly what kinds of colors. Yes?
Why would a laundry detergent do that?
You ever heard of whiter whites? Well, how do you get whiter white? You make it glow. That's how you get a whiter white. Okay? Your paper, it has material like that in it to make it glow, to make it look whiter. Okay? If I can take something and make it when ultraviolet light or blue light hits it, that it gives off light in roughly the range of white, then it appears to glow and it's a whiter white. Okay? Let me show you some examples of fluorescence. Now, by the way, much more efficient than incandescent and very low heat. Okay, so here we go. There are some different materials that will generate color based on ultraviolet. Here's a natural example of a material. This is a scorpion. Okay? Deadly poisonous scorpion encased in some acrylic. So that's pretty dead. If I take my black light, ultraviolet light, and shine it on it, what do you guys see? It's turning different color. It has molecules inside its coating that when they observe higher energy light, they give off this color. By the way, this is how people in the southwest will find scorpions out at night in the desert. They take a black light, shine it around, and you'll see this glow. Okay? Let's find a piece of paper. See how it kind of, you see the blue pretty intensely? It's kind of a whitish blue. Okay? There's material in there to make it glow. You see the lint. See the lint? Okay? That lint and or particles of detergent that are still stuck in here, because this was recently washed. And so you see that it's trying to glow. It glows kind of whitish. Your teeth will glow whitish. Okay? Different materials, a lot of living materials will glow. Also, non-living materials will glow. This happens to be vernerite, also commonly known as scapolite, a rock. Okay? You guys see it doesn't look very exciting. It fluoresces. It has natural fluorescence. Fluoresces orange in this case. Here's another stone called sodalite. This is much more common. Again, likes to fluoresce in the orange. And here's another one. This is fluorite. Again, pretty common. Seems like a lot of them like to fluoresce in this orangish color, but you actually get a whole bunch of different colors. Okay? And let me see. You see my fingernail also fluoresces? Okay? A lot of material from living things fluoresces. And we also use fluorescence quite a bit. This happens to be a Canadian $5 bill. Okay? See what they do with fluorescence? Not a watermark. It's actually fluorescent inks in there to give off an identifying mark. Does anyone have a driver's license? California driver's license? Huh?
That's €5.
€5 isn't as exciting, but you're welcome to pull it out.
So
Here's a California. What?
So that's why when you're at the airport and they check your driver's license, they shine a light.
This is what they're doing. You guys see that? You guys see that? The golden bear.
It's the flag.
It's the flag, golden bear, in 3 different colors of fluorescent inks. That's what they're checking. €5. The euros have, what they do is, there's this little purple flag here, purplish blue flag. It turns yellow. And then they also have little fibers. I don't know if you guys can see it. There's little tiny fibers. A lot of the U.S. currency has little fibers too. On the U.S. bills, thank you. On the U.S. bills, there's a little 20, 20, 20, 20, 20, or a little strike. And there's also little fibers. So those are some of the different things that fluorescence can do. Again, yes.
I was just wondering, like, when you turn in a $20 bill to pay for something, some places mark it with the pen, and if it's not real, it's supposed to turn black, otherwise it's clear. Is that because of the
No,
fluorescence,
not
or is that
fluorescence.
something else?
That's something in the paper. That's a paper material. if you guys, I don't have my wallet with me, but I can show you a 5, a 10, or a 20. It does have this stripe in there that the fluorescence picks up. All of the currency have multiple things like this. So fluorescence is just one of many things that are there for counterfeiting. Okay, just one. There's also infrared. Like on a $20 bill, there's a part of the ink that's transparent to near infrared. And so if you had a camera that only sees the infrared, it would show the stripe where the ink is missing. Okay, so there's an infrared thing. There's a fluorescence thing. There's the material that the money is made out of. There's actually some other things that are more secretive too. Okay, so there's a lot of different rules. And fluorescent light, okay, can also cause chemical change. Just like any kind of light can cause chemical change, but it can cause conformational change. And if you guys remember, I told you that when you absorb electromagnetic energy, you can either break, you can change conformation, you can rotate, you can vibrate. Those are all the different things you can do. Well, this is an example. If I take these white beads and I shine my ultraviolet light on them, the structure changes temporarily and they get color. Okay? So these are what they call UV sensitive beads. You can make jewelry out of these. A lot of kids do this. Then when you go outside, if it changes color, you know that you're being exposed to ultraviolet light and you could get sunburn. Okay? These are kind of fun.
But they wear it out after a while. They stop changing back and forth.
The good ones seem to last a heck of a long time.
We've had some problems. We're getting cheap ones at the Science Museum, but we've all had them around.
We've had them for some of the ones we've had for years, and they're still working. So I think it depends on which ones you get. And certain colors work a lot better than others. Okay? So here it is again. Here's another way of representing this idea of fluorescence, because I need you guys to be aware of the different ways of representing this idea. In this case, they show you that they're putting in purple light, and this is giving off blue light, blue fluorescence. So it just depends. Different materials will give off different colors of fluorescence. This is another way of representing it. You absorb UV photon. It causes an excitation of the electron. And then when the electron goes back, it gives off energy again. Okay? Always, the energy emitted in fluorescence has to be lower or higher than the energy put in. Lower. It's not a perpetual energy machine. It doesn't generate energy for nothing. Okay? Always the energy is lower. And this is a way of showing that if this is representing the energy of the electron, when the electron is in the ground state, it absorbs, for example, a photon of blue light, causing it to excite to an excited vibrational and electronic state. So it didn't go to the bottom one here. It went somewhere up here. You get some relaxation in vibration. This is vibrational relaxation. And then the only thing it can do is to jump all the way back to the ground state. In this jump, you notice the separation here is smaller than the separation here. Because the separation is smaller, that equates to less energy. Less energy has to be a lower energy photon. Okay? So, if I can excite something with red light to emit fluorescence, what color of fluorescence will emit? Trick question. Infrared. If I excite something with green light, what colors could it emit? Sorry?
Yellow through red.
Yellow through red. If I excite something with blue light, what colors could it emit? All the other colors. Right? Green, red, yellow. Does that make sense? Yes.
How do you figure that out?
Okay. So, the easiest way for me to figure it out is to think of, I like to think of the word Roy G. Biv. You guys have heard of that? Yeah. If you write down Roy G. Biv, Roy G. Biv, which side of this has the high energy and which side is low energy? This is low. Okay. This is low. And this is high. So whatever color I use to excite with, if I use blue, I can get the colors that are of lower energy. If I use red, I can't get any of these. I have to go to infrared. Okay? If I use ultraviolet, I could get all of these. Okay? That's how I like to remember it. If I'm ever confused, that's what I go back to. Okay? Low G big. That's the easiest way to think about it. Okay. So, phosphorescence. Phosphorescence is our infamous glow in the dark. Okay? Glow in the dark materials. So, you guys have seen little stars, little t-shirts, whatever it is that you might have had with glow in the dark materials. So, I'm going to take my little glow in the dark material right here, and I'm going to shine red light on it. Let's see how exciting the thing happens. Was it exciting? Very exciting, right? So that was my lowest energy light. I'm going to go a little higher in energy now. I'm going to use green light. You see a little bit happening? Okay, now I'm going to use blue light. Okay? And now I'm going to use ultraviolet light. Okay? So, what can you tell me about the different colors of light that I use to excite this and what happened? First of all, what color is being emitted? Yes, you had a... The longer it stays, and also the brighter it was. So, yes.
Is that why you're supposed to like go outside and shine together from vapors and
Yeah, exactly. Because, I mean, incandescent light will work too, but it depends. The sun's always going to be stronger. There's going to be more higher intensity of those wavelengths. I can also take my white LED. Will the white LED work? Why? Sunlight works, but this has got all colors. So, because it has all colors, that's what. It doesn't work quite as well as the blue or the ultraviolet, because those are actually brighter in those wavelengths than the white is. Huh? We went to a museum, a rural museum up in Northern California, and we actually made a whole wall of this stuff for them. And they go through and the kids draw. And you can use a flash to shine yourself, your pattern out here. Some of you may have gone to the exploratorium and seen that kind of a thing. Okay? Now, I want you to notice something. Let me turn off the lights one more second here. So, when I do this, what do you notice about the light? Oh, it's focused because this was focused. Does it? Now, you see that, and now let me show you fluorescence. Here's my scorpion. You notice any difference? Yes.
It stays a lot longer.
It stays a lot longer. Okay? It gets dimmer and dimmer and dimmer, but it lasts a long time. That's the difference. Fluorescence is immediate. The moment you turn off your light source, it's gone. On the order of nanoseconds, it's gone. Okay? But phosphorescence takes time to decay. It can take anywhere from milliseconds to 100 seconds or a couple hundred seconds, okay, for it to totally go away. I can still see some on there. Okay? And it's because we showed you before fluorescence worked like this, that you get something jumping up, you get a relaxation, then you get lower energy emitted back out. This is called the Jablonski diagram. It's a more complex diagram than the one I just showed you before, but again, lower energy, higher energy, these are different excited states. This is the electronic state, and these are the vibrational states. All this is showing you is that this is how fluorescence works. Gets absorbed, relaxes, gets re-emitted. Phosphorescence goes through something called the excited triplet state. It's also known as a forbidden state. Why they came up with all these names. It's a forbidden state. It isn't supposed to happen very often, but in certain situations it does, and then it leads to the photons hanging out around here and then being re-emitted and giving rise to phosphorescence. Because they stay in here for a little while, some photons escape right away, some take a little longer, and that's why the phosphorescence lasts. Okay? That's why. That's the big difference. Okay. Then we have chemiluminescence. So, chemiluminescence is basically what happens in those light states. I think you mentioned it earlier. Okay? You've got a chemical reaction that causes some atoms to be excited, and then when they come back down, they re-emit light in a chemical reaction. You get A plus B going to some excited state intermediate, which then yields your products plus light. Now, if chemiluminescence happens in something living, then it's called bioluminescence. Okay? And bioluminescence, have you guys ever seen the jellyfish? You guys ever gone to the Monterey Aquarium or somewhere else and seen the jellyfish? They've got kind of those black lights on them, and those black lights make them kind of glow. They've either got a little blue or a little green glow. Okay? That tends to be, they add the black lights to enhance it because they also usually have fluorescence in them. But they can just make them, they'll just glow by themselves. Okay? I don't know if you ever had the experience of, I was in Mexico down in Baja. I was at a beach. It was pitch black on that beach. I was walking along the beach right near the water line, and my footsteps glowed. Okay? That was tiny little crustaceans that were in the water that was washing back and forth that were bioluminescing. And when I was, in a sense, scraping against them, they were getting excited in some way, and that was causing the bioluminescence to happen. They were giving off light. Yes?
I like in India, I mean, it's called like red tide or something when it comes in, and like coffee or something. I don't know, it's just it blows blood up, right?
Yeah, exactly. Same thing, bioluminescence. And usually it's with the waves when they're getting kind of stirred up. Okay? In Bermuda, when they flush the toilets, they glow green. Okay? Because they use seawater for flushing the toilets. Okay? And sometimes those particles are in there, and so it'll glow green. Okay? So that's bioluminescence. Now, this is a way in which chemiluminescence is used. You use something called luminol. Luminol, when you spray this material and there's any kind of blood around, or actually any kind of iron source, it'll glow for about 30 seconds. That's another chemiluminescence reaction. If you guys watch CSI, they're in the room and they're spraying. It's dark. They've also got their black light, because most bodily fluids will fluoresce. That's why they have a black light. Okay? Blood, you can see really small traces of blood. You can make them glow by just spraying luminol on them. And it would look like this. Here's your regular carpet during the day. You turn off the lights and you spray the luminol, and you can see the traces of blood. Now, problem is it shows you traces of iron. Because there's iron in blood, that's what the luminol is reacting with. So, if you were trying to figure out if there was traces of blood in an iron factory or a place that generates a lot of iron dust or filings, it wouldn't work very well. You'd think there was blood everywhere. Okay? But if you're somewhere where that isn't the case, then luminol will work. Did you have a question?
The intensity of that is because intensity is supposed to decay over time, like if we have iron dissipate.
No. Iron is a metal, it'll stick around. That's the beauty of that technique over some of the other techniques. So if you keep on repeatedly washing the carpet, it can go away. But unless you put some other material that will bind up the iron irreversibly, which is pretty hard to do, I guess you could spread sulfur. If you made it into an iron sulfide, that would be pretty hard. But you'd have to be pretty thoughtful about this. I'm going to now spread sulfide powder everywhere. Okay, and the last one. Black body. Okay, so something that's counterintuitive is that if something gets hotter, it'll turn. This part's kind of intuitive. It goes from not seeing it to black. From black to red, just like we saw with those space heaters. And as you get more into the yellow, it gets hotter. As you go more into white, it gets even hotter. And then actually, something will turn blue. That's even hotter. Okay? It's hard for us to think of blue as signifying hot. But if something is blue hot, it's really, really hot. Okay? And let me show you how this works. Okay, let's see, where is it? Right here. Okay. So, what this allows me to do is something called the Spectrum Explorer. I can add something called the black curve. And what it'll do is it'll show me the range of wavelengths, something that is of this temperature, or I can change the temperature, the range of wavelengths it produces. This shows me, this is infrared, this is our spectrum, And this is ultraviolet going off into X-rays. Okay? And here's the wavelength. 1 times 10 to the 2 nanometers. This is 100 nanometers. This is 800 nanometers. Okay? So, what temperature are we in Kelvin? Body temperature. What's 0 centigrade in Kelvin? You guys remember? 273. What's our standard body temperature in centigrade? That's in Fahrenheit. In centigrade, it's about 37. 36, 37, okay. So add that to 273, and you get 310. Okay, so let's type in 310 here, and let's see where we emit. Well, let's move this down here. 310. Oops. I thought I could, but it's not behaving. Oh, there we go. Okay. There's our emission curve. Ooh, guess what? We don't emit in the visible light range. This is our visible light range. We don't emit 400 nanometers to 700 nanometers. We don't emit any light there. We knew that, right? Because we can't see each other in pitch black. We don't emit any visible light. Now, this right here shows me where the peak is of our emission. It says 9.33 times 10 to the third nanometers. So 9,337 nanometers is where our peak of emission is. That's in the far infrared. Okay? But, now if I raise the temperature, by the way, this shows you roughly an approximation of the color that this object would appear. And it can't show you infrared, so it just shows it to you as that kind of red. As I raise the temperature, you see I start giving off light in the visible range. And now something would appear orange. Something that's 1609 degrees Kelvin would appear orange to our eyes. Okay? As I go up in temperature, it starts to appear even stronger orangish yellow. And this is where we're getting sort of like our heaters. Our heaters are in that red, orange-red color. So they must be somewhere between 2000 and 2500 Kelvin. And now we go up higher. Now it starts to look more yellowish, more white. Now it's white hot, the object. And when it's white hot, see it's emitting some blue, but it's emitting even more yellow and orange, and some red. And if I go even hotter, still look white, but now I start to look more bluish white. Now I start to look blue. Because you notice what's happening as I go hotter and hotter, the range of wavelengths I'm emitting as a black body emitter is moving towards higher energy, the peak. So I have now the most is blue, and I have less of the other colors, so therefore I appear more blue. And I just keep going until I can get much higher energy as I get hotter and hotter. Now, if I take the spectrum of the sun, it's over here, data file, I put the sun on there, that's the range of wavelengths the sun emits by the time it gets to Earth. Yes?
Does it depend on, like, what the material is?
No.
So, like,
temperature.
Is actually that hot when you're putting something like a flame when it's blue?
That part of the flame, that little part of the flame is very, very hot. Okay? But you're also getting some distortion. See, so I should qualify. You see how the sun doesn't have this nice little rounded shape? This is called the idealized black body radiation curve. This is the reality, because the reality is there are materials in there. There are gases in the sun, and those reactions generate some of their own colors, some of their own wavelengths. Some absorb, some emit. So you get this squiggly. Some of what you're seeing in that blue flame, it is the hardest part of the flame, but it isn't exactly the temperature of this black body radiation curve, because partially also what's happening is emissions from the gases that are used for lighting your flame. Okay? This is idealized. So if I want to figure out what the temperature of the sun is, roughly, I move this curve until it's as close as possible. I'd say somewhere around there. So this is telling me that on average the temperature of the sun is 5,900 degrees Kelvin. Okay? So I can tell the temperature of something, an astronomical body, just by matching it to a theoretical black body curve. Okay? So effectively, I can tell the temperature of most things just by seeing what color they are and what range of wavelengths they emit. Okay? Any questions about that? Okay. So that you saw. Okay. And then you guys remember, that's how this thing works. This thing you put across your forehead, and it's measuring the black body emission, 99.1. 98.5. Okay? It's getting the temperature based on matching it to one of those black body radiation curves. And that's how this thing works. Okay. So, just as a recap, we saw that we can make light through incandescence, electroluminescence, which was our LEDs, lasers, fluorescence, phosphorescence, chemi and bioluminescence, and then there's the pure form of incandescent, which is specifically called black body radiation. So this is really related to incandescence, okay? It's the same thing. Okay? It's just a idealized form of incandescence. So with that said, now we're going to get to characterize light sources. Okay? We're going to take about 25-30 minutes. You guys are going to divide up in groups of 3. I have 13 of these highly expensive pieces of equipment. Now, these are NASA spectroscopes. We thank NASA every day we use these. Okay? They're actually very, very nice. They have a grating in here. The grating takes light and separates it into its component colors. That's what the grating does. And what we do, you see a little slit here? We are sampling the light that goes through that little slit. And there's a, let me see, there's one, some of these have that open. Oh, I guess they don't. In here there's numbers. Okay? They range from, let me see, they range from 6,000 to 3,000. Those are angstroms. Astronomers, that's who these kinds of people are, like to use angstroms. I'm more of a chemist, biochemist. I like to use nanometers. So to convert from angstroms to nanometers, we take off a 0. 3,000 is 300, 400, 4,000 is 400. Okay? So you're going to be looking, you got in your worksheet, you're going to be looking at all these different light sources, but now I'm going to find out what wavelengths are in there. So, why don't you guys divide up into groups of 3, and here, you can each have one of these, and I just want to make sure you guys know how to use these properly. Here's one. Okay, so we're with them. You guys get started. Actually, you guys get, let's see, how many groups do you have? We'll have to have one group of 4. You have, let's see, 3. So, go ahead and look at the fluorescent lights above you. Rate these to these ratings. See what you see. And I'm going to have a couple more of these, I'm sure. Take a look. Here's the extras here, so. Look at the fluorescent lights and somebody tell me what you see. Here's an extra one. Here's an extra one. Actually, wait a second. I'm going to give you this one. You get 2 different ones. That's the same. You're going to charge it for that. Here we go. Here's another one over here, guys. Somebody tell me what you see when you look at those fluorescent lights through that slit.
A couple narrow bands.
Okay, the way you have to... Yeah, you can hold it if you want. Can somebody tell me some number that they see that there's a band at?
650.
650, okay. So do you guys see what you do on your sheet? You've got a scale on the bottom, nanometers. You make a little mark for what you saw for that light source. Okay? So now, you just have to go and stand up, grab the different light sources you need out here. Who wants to be the one that breaks the light fix? Who wants to break the light fix? Here you go. You, I want you. All right, break it. Get it going. We're going to discuss a few things now. We're going to discuss a few things now as a group, and you can fill in some parts that you might have missing. let's just go down that chart, and I just want to hear somebody tell me kind of what they saw. So let's start. Let's see. It starts with sunlight. The wavelengths.
We have from 440 to 630.
Okay. Anyone else have something different?
We went to probably a different one, but ours was pretty bright, so it got a little bit narrower, and it was like 420 to like 670.
Okay. Pretty much the sunlight, the big message is it covers the spectrum that you can pretty much see. Alright? There might not be quite as much intense blue or violet in the sunlight that you saw. So that's why you might see that it was not so bright on the edge. Okay? But it pretty much has the whole rainbow. Okay, what's the next one on there? Incandescent. What did people see? Yes?
It looks like the full spectrum against very bright.
We have the full visible spectrum. Again, it has all the colors of the rainbow. And you saw everything in there. Very similar to the sun. And how does incandescent light compare to how sunlight is made? How do you make incandescent light?
Black light.
Sorry?
Heat, black light.
You're making something really hot and having it radiate. How does the sun make its light? Something really hot, giving off electromagnetic waves in the big range of the spectrum. Okay? Similar. Okay. Next one. Halogen. What do you guys see? Yes?
Pretty much the entire range of light, but it was concentrated a little bit more towards the bluish than incandescent.
So remember, incandescent lights tend to look a little bit more yellowish, and the halogen light tends to look a little bit more bluish, right? So that makes sense. There's a little bit more blue in the halogen light. Okay? How about the white LED? What do you guys see? Kind of like the sun. Was it as broad of a spectrum? Did anyone see anything different?
It was similar to the sun, but it wasn't as broad of a spectrum. I got from 430 to 660.
Okay. Did you see any variation in the brightness in the spectrum? Anyone see anything like that? Any variation? If you had a more sensitive instrument, which you guys will be utilizing later in the course, you would actually see that there's a place kind of around, I think, 470, 480, where it dips. So it's like really bright, dips, really bright, broader, and dips. Okay? It's hard to see with those tools that you had. What's the next one?
Colored LED.
Colored LED. What's something you can tell me, no matter what color you used, what is a characteristic of LED light? Is it broad like the sun? Of a specific color LED light. Is it broad like the sun? Is it like a laser? Or is it something different? Somewhere in between. What kind of width in terms of nanometers that you guys measured for?
Like 50 nanometers.
Like 50 nanometers.
One really bright spot.
One really bright spot in the center. So the basic idea is that an LED light of a specific color has some breadth. It isn't just one specific wavelength. How did that compare to your lasers?
So very narrow band.
Did anyone else see a narrow band with the lasers?
Yeah.
What wavelengths did you guys get for the lasers?
Between like 530 and like 640.
Sounds great. They actually tell you on the side of the laser, the green one tells you that it's 532, okay, and the red one tells you that it's somewhere around 650. So you're close. Okay, so big point here, very important. Laser, very thin, monochromatic. LED, somewhat monochromatic, can be made. Like the blue LED is blue and the green is green, but broader. Somewhere between, anywhere usually between 30 and 100 nanometers in breadth. Just depends on the type of LED. Okay, 50 is about right, about average. Okay, incandescent, halogen, much broader. Okay, whole spectrum usually. Okay, what did you guys notice about the fluorescent lights?
There
So there are multiple wavelengths, some broader, some thinner. Okay? So these look white. How come they look white? And the sun looks kind of whitish yellowish. How come these look white? The sun had all the wavelengths in it. These only have 5 or so. Any thought?
The interactions of the colors.
The interaction of the colors. Your brain only sees red, green, and blue. Okay? You have detectors for red, green, and blue. So your brain says, oh, they're all about equally stimulated. Oh, it's white light. Oh, only the blue one's stimulated. It's blue. Oh, only the red one's stimulated. It's red. Oh, the blue one and the red one are stimulated. It's purple. Okay? That's basically how our brain works. It doesn't know the difference between yellow, that's pure yellow, and yellow, that's a mixture of red and green. So if I shine a red light and a green light at you, equal intensity, your brain thinks yellow. If I shine a yellow light that's just purely yellow, your brain thinks yellow. Okay? So your brain can't distinguish, can't really tell when colors are pure. Huh? We don't have that capability. That instrument could tell you the difference between red and green making yellow and pure yellow. Okay? And more advanced versions of this can tell you fine nuances. The fluorescent light just takes advantage of those phosphors and fluorescent pigments that are inside the tube to make all those different colors that mix together to give you the appearance of white. Some of these fluorescent tubes look more yellowish, some look more greenish, some look more bluish. It's just a question of what mixture they used in generating those wavelengths. Okay? Okay, was there something? The scorpion. What did you guys see for the scorpion? Which was the mock for fluorescent paint. What wavelengths did somebody see? Anyone back there? Tell me. What'd you get? 450 to 520? Okay. Is that what other people got? Some people I think got more. Some people might have gotten less. Okay. It was kind of hard to see. It's kind of faint. But it looked to me yellowish, greenish. So that's the range of wavelengths it was producing. Okay. Anything else you guys want to say? Any other comments? The big point here is if I use different types of light and I have them interact with tissue, as we do in biophotonics, those characteristics matter a lot. How many wavelengths does that light produce? How bright is that light? Is there fluorescence involved in what I'm seeing? All those things matter in what I'm going to see. Okay? So those are different sources of light. Any other comments or questions? Okay. So let's do a quick look at light interacting with matter. So what happens when photons hit matter? If a photon comes in, hits something, what could happen to that photon? What are some ideas? The photon could? Yes. It could go through or bounce back. Okay, some other ideas. Yes.
It could interact with material in some way.
How? Give me some ideas.
Photoelectric effect. It could excite electrons.
Excite electrons, okay.
Reflect, refract, or...
Refract, which means what?
It's like the diffraction rating is refracting light, isn't it?
Mm-hmm.
Where it bends the light of certain frequencies in different directions.
Okay, anything else? What could also happen to the photon?
Transmit.
Could transmit. What else?
Can it break?
Can the photon break? Mm-hmm. The photon itself can't break. I'm not sure what that would mean. Now, the photon can disappear by being converted into something else. It can be absorbed and converted into heat, or it can be converted into breaking some kind of molecule, some kind of bond. So it can do that. That's what you mean by break. Anything else?
It can strip another electron off.
Can strip another electron off? Yeah. Can do all those different things. So let's look at those specifically. So, reflection. You guys know that the angle of incidence is equal to the angle of reflection. Okay? It comes in one way, like if I point this here, let's see, it should be reflecting somewhere over there. Where did it go? I'm not having much luck with this. Oh, there it is. You guys see it on the wall? So this angle would be the same as the angle going over there. Okay? Plain old reflection. Easy. There's no change in wavelength. Okay? No change in wavelength at all. It can be transmitted. Like if I put it through water, glass, or plastic. Again, no change in the wavelength or in the color. It just goes through. Okay? It didn't really interact with much. It can be refracted. Okay. Now, in refraction, if my photon goes through a material that's denser than the material it came from, it gets slowed down. Imagine, these photons are traveling. They're traveling through the air, nothing much blocking them, nothing slowing them down, they go fast. Now they come upon diamond. Diamond is very dense. They slow down. That slowing down causes the light to bend. Okay? Not if you're going straight through something, but if you're coming into something at an angle, the light will bend. So, for example, if I come in here, this is air, and this is glass. If I'm shining my laser like this, I get into that material, and it bends towards the normal, towards the line that goes right through the material. Okay? It comes in, it bends towards it. Let me show you a little demo. Put this in the way. Okay, so this is showing if I'm in, let's go the other way around first. Okay, air to water. Okay, so this is my laser. I'm shining it on a surface with water. Okay? It'll go on the surface of the water and bounce off at the same angle. That's my reflection. It'll refract. It'll bend towards the normal because water is denser than air. Okay? Do you guys think diamonds are denser than water? Yeah. So I'll go in here and I'll shift to diamond. And lo and behold, it bends even more. Okay? Now, I can take advantage of this if I have something in, let's try crown glass. And then I put, the other side I put air. So, if I have my light, my laser shining through a piece of glass, okay, you'll notice that it doesn't get into the air until the angle becomes such that it can actually come out. It's in a higher density medium. If it goes out into the lower density medium, it'll bend away from the normal. If I go from high density to low density, I bend away from the normal. If I go from low density to high density, I bend towards the normal. Okay? Because of that, I can actually trap the light inside the glass rather than having it escape outside of the glass. And I'll show you a diagram of that in a second. Here it is. Okay? This is showing you how a fiber optic works. You guys ever heard of a fiber optic cable? Okay? Fiber optic cable, here's the glass part, and this could be air, usually it's some other type of material with a lower index of refraction, meaning it's less dense. I can make the light come in anywhere along here with a laser, and it'll always stay trapped inside the glass. So I can, this is an example of fiber optic with air on the outside. See, I put my laser in, and it can bend and stay inside, never escaping outside of the glass. I can trap it because of refraction. Okay? Because the angle is too shallow for it to escape. If the angle was steeper, like if the laser was coming in like this, it would escape. Some would escape and some would bounce inside. But because my angle is not steep, I can keep it trapped and I can make it turn and trap the light inside the fiber optic. We use fiber optics a lot in biophotonics to get light into your body. Okay? If we want to bring laser light, for example, into the arteries that are feeding your brain, we can snake it through there. Okay? In a fiber optic, and then deliver the light where we want to deliver it. That's taking advantage of refraction. So the other thing that can happen is scattering. And scattering is basically, I've got an incoming photon, it hits this material, and some of it goes to the side, some of it goes forward, some of it comes back. And it basically varies as the function of the ratio of the particle diameter to the wavelength of the radiation. So depending on what light I bring in and the size of these particles that make up this material, I'll get different amounts of forward scattering, side scatter, back scatter. Let me show you an example of that. Okay, let's try this here. So this is to introduce what you guys are going to be doing Wednesday. So, first let me show you just regular scatter. So here's my laser beam, right? Regular laser beam. I'm going to now, let's see, can you guys see that? Let me bring it over here a little more. See what happens there? That's scatter. I'm shining the laser light through a piece of Scotch tape. And that's what it does. Let me see if this looks better. No. You guys see what it does? That's scattering. You see how the laser light just got split all over the place? It's going everywhere. Okay, that's what happens if I have a medium that has all kinds of randomized spacings on molecules. I get this scattering. This scattering phenomenon. Now, I've got some hairs that were doing it in prior years here. And the hairs are horizontal. Okay? They're over here over a little hole. And I'm going to shine my laser light on that hair, which is the equivalent of shining light onto a little tiny slit. This is a hair, the equivalent hair. It's the same thing. You get the same results. What do you guys think we'll see when I do this? I'm going to shine the light. The hair is this way. What are we going to see? I got to shine it way out in the back here. Let me go back here. There it is. I'm shining on the hair right now. What do you guys see?
Vertical stripes.
So, kind of weird, right? You'd think a hair would just show me some light and a black spot where the shadow of the hair is. But now this is a laser, which means the light is of a single wavelength and it's coherent. So waves add and subtract as they go around the hair. And actually the brightest spot is in the center, right where the hair is. And the hair is horizontal and the pattern is vertical. Okay? And see those separations between the dark spots? Those separations are going to equate to how thick this hair is. And that's what you guys are going to be doing. I've got a little bit better setup than this for you guys to use. This gets a little hard. There's another hair. That's a thinner hair. And here's a thicker hair. You guys see any difference? Thinner hair. Thicker hair. You saw a difference? Difference in the spacing of the pattern? And that's what's going to equate to figuring out the size of your hair. And those are the two demos we just did. And I'm going to show you a little applet here that shows you this too. Here it is. This is showing you an aperture which behaves the exact same way if this is a hair and there's nothing on the sides. This is supposed to be the waves coming through the aperture. And this is the pattern that you see on the wall. Let me turn down the lights again. See, that's the pattern that we saw? Bright, dark, bright, dark, bright. Okay? You guys see that? If I change the size of the hair, a smaller hair makes them spread out more. A bigger hair makes them come closer. Okay? And if I change the wavelength, let's actually make this a little bit like this. 1 second. There's the blue. Oops. Meetings, meetings, meetings. If I use red, what happens to the pattern versus using blue?
It spread out more.
Which way?
Red spreads it out more.
Okay? So, what we're going to do when you guys come in here on Wednesday is we're going to actually try it. I have red lasers, green lasers, and a blue laser. Okay? And you're going to measure the thickness of your hair with all three. Okay? And this is kind of a diagram showing you how this works. If this is the slit, or you can think of it as the hair, you get photons that came to the edge, to the two edges, added together because they traveled the same distance and they gave you this bright spot. If instead you have a photon coming from here and one coming from here, they travel different distances, they cancel each other out in the way that the waves add. So these waves add and subtract, giving you rise to this pattern as they go around your hair. And they actually go around your hair and add, subtract. They behave just as if there was nothing there but a slit, things on the other two sides. Okay? You saw that. So basically, interaction of light with matter, this is the absorption. This is the other type that we discussed briefly before. This is the loss of light as it passes through material. Generally, this is due because the energy has been converted into some other form. And pretty much what we're interested in this class, for the most part, is taking photons and having them interact with matter and generating light of some kind. That's what we tend to study the most. Okay? And the main things we look at are reflection, absorption, transmission, scattering. Those are the main phenomena that we tend to look at in biophotonics. Reflection is the light coming off. Absorption is the light that's been absorbed and either just disappears or gets converted via fluorescence into some other color. Transmission and scattering. Okay? All of those are happening simultaneously with all things. It's just a question of which one of those is dominant, or which one or two of those are dominant. So with that said, today we covered light sources and a little bit of light-matter interactions, and we'll continue Wednesday with the light-tissue interactions, but we'll start with the hair. So make sure you have something to write into. You're going to be taking notes. You're going to be trying to figure out what sources of air there are and what you're doing. And I'll be passing you out sort of an idealized report format for what you guys write out. Okay? Thanks, you guys.